Okay, let's talk about the particle nature of light. So light actually comes in packets called photons, or sometimes called quantums. Um, so even though light behaves as a wave as well, it's both. It has both particle and wave nature. Okay, so the wave nature has to do with its wavelength and frequency. Okay, which then can be tied to the types of light that you have. But that wave nature is actually also related to the particle nature. So it is related to these packets of light called photons. But the photons, um, the reason we know that it behaves as these packets of particles, or these particles that we call photons, is because of the way that light passes energy. Okay, um, because it passes energy off in specific quantums. Okay, in specific packets. Okay, certain amounts of energy. It is quantized. It isn't a continuous amount of energy that gets passed. It's in these individual packets, and those we call photons. Okay, um, and so when we quantify the energy of light, it's telling us about these individual photons. Okay, um, and that the energy of each photon is actually directly proportional to the frequency of the light. Okay, so we can actually quantify energy of the photons using the frequency. Okay, and so there is a link between what we see as this particle nature and the wave nature of light. And so the relationship is just E equals h nu. Okay, and the E is our energy of our photon. The h is Planck's constant, and the nu is our frequency. Okay, so I didn't label those two. Thought E hopefully is kind of obvious, but I'll write that down. That's the energy. Okay. And really it's of a photon. So you have to be careful. It's not of the entire wave, okay? Because the entire wave is made up of continuous photons, okay? We've got photon after photon after photon coming from a light source, okay? And each individual one has this energy, okay? And then the nu, remember, is your frequency, okay? And so if you know your frequency, all you need to do is multiply it by Planck's constant, which is a constant, as it says in the name, which is given below. Okay? Or if you know the energy of a photon, you can divide it by Planck's constant, and that'll tell you the frequency of that particular light. Okay? But they're directly proportional, meaning the higher one is, the higher the other is. Okay, so if you have a high frequency, you have a high energy. Okay, or if you have something that has a lower frequency, it's going to have a lower energy. Okay, those are directly proportional to one another. Now, we can also relate the energy of a photon of light to the wavelength of light, but these are inversely related because frequency and wavelength are inversely related. And so if energy is directly related to frequency, it's got to be inversely related to wavelength, because it's got to be opposite of one of them if those two things are opposite of one another, essentially. And so we do have a relationship that we can use to calculate between energy and wavelength of light, and that is E equals hc over lambda. And really that equation is just a combination of that first one and the equation that relates frequency and wavelength. Okay, so really it's a combination of E equals h nu and c equals lambda nu. Okay, so if we were to rearrange this speed of light equation for nu is equal to speed of light over lambda. Okay, So you can take this and plug it into here. And if you do that, that gives you E equals H times C over lambda, which is the same thing as E equals HC over lambda, like I have written there. Okay. So again, E is the energy of the photon, H is Planck's constant, C is the speed of light. Okay. Which is a constant, okay? And so usually we would use 2.998 times 10 to the 8th meters per second for that. And so that's really the speed of light in a vacuum, but that's good enough for general purposes. And then we have wavelength. Okay, so you can calculate the energy of a photon of light from the wavelength or the frequency of that light. You don't need to know both, okay? And so if you know one of those, you can calculate the energy. Or if you know the energy, you can calculate the frequency or the wavelength, okay? So those three things are actually all tied together, okay? So even though two of them really are telling you about the wave characteristics of that light, and the other one is telling you about the particle nature of that light, they're still related to one another because it's all light. Okay, so it's all electromagnetic radiation. So really, for a light source, you only need to know either the energy of a photon, the frequency, or the wavelength. Once you know one of those, you can actually calculate the other two pieces of information using the speed of light and Planck's constant. Okay? So they're all tied together. So when you're thinking about electromagnetic radiation or the electromagnetic spectrum, which consists of radio waves, microwaves, infrared light, visible light, ultraviolet light, X-rays, gamma rays, all of that stuff is part of the electromagnetic spectrum. All of those things have some wavelength, some frequency, some energy, but they all have this general relationship to where the wavelength and frequency are inversely related. So the stuff with longer wavelengths always have lower frequencies. Okay, so you see on the side where radio waves are over to the left, that is labeled at the bottom as having long wavelength, right? But a low frequency because those are inversely related. But as you go towards the right, where we've got gamma rays, that has short wavelengths, thus high frequencies, okay? And since energy is directly related to frequency, where you've got low frequency over on the radio wave end of that spectrum, you have low energy. Where you have the high frequency over at the gamma ray end, you have high energy, okay? Meaning photons of gamma rays have much higher energy than radio waves, okay? And this is actually in order. So radio waves has the lowest energy photons, microwaves is the next, and then infrared, then visible, then ultraviolet, then X-rays, then gamma rays, okay? And you can talk about what has the longest or shortest wavelength and lowest and highest frequency based on this diagram here. I think it's usually helpful to understand them in terms of energy, because energy is kind of what we get from it. Okay, so if light shines onto a sample, or say on us, the higher energy it has, the more it can do. Okay, so if you are throwing a bunch of energy at something, shining this high energy source on something, then it could potentially, say, break chemical bonds, okay, which may not be a good thing. If it's our skin, if it's the molecules on the surface of our body, or even if that radiation passes through and it starts breaking bonds, that can be a problem. And so it's generally good to have an idea of how the energies of these things relate. So radio waves and microwaves are low energy, so they don't, do a ton of damage. Well, luckily, radio waves are passing through all the time, right? That's how we get our radio signals, our TV signals, and those are low energy. They're not hurting us. Um, and then like infrared, that's used in like remotes, or um, that's actually also associated with like night vision and stuff. All of that stuff is lower energy than visible light. And above the energy of visible light is ultraviolet, so like from the sun. So that's why you get like a sunburn if you're out in the sun too much, okay? Because it's actually damaging molecules on the surface of your skin, okay? And so it's causing that sunburn. And that's, and x-rays are higher energy. That's why they don't let you just constantly get x-rays. And that's why the person who's assisting in giving you an x-ray, when you get an x-ray, they shield themselves because they don't want to constantly be exposed to this high energy radiation. And then gamma rays, that usually you only hear about gamma rays when you're talking about nuclear reactions. And those are extremely high energy forms of radiation. Okay, so it's good to just have a general sense of what are all the different forms of light. And so that's the entire electromagnetic spectrum. All of that stuff is light. All of that stuff has wavelengths and frequencies and energies associated with them. Okay, so let's do some calculations related to the particle nature of light, so the energy of the photons. So this first one, I say, what is the energy of light with a frequency of 2.58 times 10 to the 6th hertz? Okay, so we have a frequency, so nu is 2.58 times 10 to the 6th hertz. And we want to know the energy. Okay, so the energy of a photon of that light is really what we're looking for. And so we can get that by using E equals h nu. Okay, now I didn't give it on this slide, but you could go back and look, and Planck's constant, or h, is 6.626 times 10 to the negative 34 joules times seconds. Okay, and so all we need to do is plug into this equation. So E is going to be equal to 6.626 times 10 to the negative 34 joules times seconds times 2.58 times 10 to the 6th hertz. Now hertz is the same thing as 1 over seconds. So I'm going to rewrite that so you can see the seconds cancel, and we're going to get an energy in joules. So it's 6.626 times 10 to the negative 34th times 2.58 times 10 to the 6th. That should come out to 1.71 times 10 to the negative 27 joules. Is the energy of that light. More specifically, that is the energy of one photon of that light. So when you actually have that light source on, as the light is coming out, there's actually constantly photons. So there's just, that energy is constantly being essentially emitted from that source of light. Okay, let's do another one. So this one says calculate the energy of light with a wavelength of 250 nanometers. Okay, so we want the energy, and we have a wavelength of 250 nanometers. And we can relate energy and wavelength by using the equation E equals hc over lambda. And so we need the constants. H equals 6.626 times 10 to the negative 34 joules times seconds, and we need the speed of light, so 2.998 times 10 to the 8th meters per second. And then we just plug it into that equation. So E equals H, so 6.626 times 10 to the negative 34 joules times seconds times the speed of light, so 2.998 times 10 to the 8th meters per second divided by the wavelength, so that's 250 nanometers. But then let's look at our units, okay? So we have the seconds are going to cancel. And then I have joules, meters, and nanometers. So I have a problem. I'm looking for an energy. It should come out in joules. And so my wavelength is in nanometers. You could first convert it to meters, so it will cancel units in this equation, or you could do it right within. Since I already wrote out the equation and didn't convert first, I'm going to do the conversion in the equation. So I'm going to put in a conversion here. So I want to put nanometers on bottom, so it'll cancel, and meters on top of that fraction. So 1 meter is 10 to the 9th nanometers. And so then I'll have meters that cancel with the meters that are on the top. And my answer will come out in joules. So here I'm going to take 6.626 times 10 to the negative 4th times 2.998 times 10 to the 8th and divide by 250. And then since I have 1 over 10 to the 9th on the bottom, that's the same thing as multiplying by 10 to the 9th on the top. And so that looks like it should give you 7.9 times 10 to the negative 19th joules. So I rounded to 2 sig figs because that 250, I don't know if that 0 is significant or not, so I assume it's not. Okay, let's do one. Now this last one says, what is the wavelength of light with an energy of 7.86 times 10 to the negative 29th? So I want wavelength this time. Kind of turned out looking like an X. So wavelength, and then energy is 7.86 times 10 to the negative 29th joules. And so I can use the equation E equals hc over lambda. But I want lambda, so if you want, you can first rearrange it. So wavelength would be, if I multiply the wavelength over and then divide the E back to the other side, it would be hc over E. Okay. And so I'm going to plug into that. So my h is 6.626 times 10 to the negative 34. Joules times seconds, and then the speed of light's 2.998 times 10 to the 8th meters per second over my energy 7.86 times 10 to the negative 29th joules. And then I've got to watch my units. Joules is going to cancel, and then seconds is going to cancel. So my wavelength is going to come out in meters. So I can type this in now, 6.626 times 10 to the negative 34 times 2.998 times 10 to the 8th divided by 7.86 times 10 to the negative 29. And if you're not using your scientific notation button on your calculator, make sure you put that in parentheses. Okay, so let's see, that gives me a wavelength of 2. Let's see, I want 3 sig figs here, so 2.53. Oops. 2.53 times 10 to the 3rd meters. Okay, seems kind of big, so maybe I typed that in right. Try it again just to make sure, since I don't have the answer given on this slide. Okay, looks like that's good. Okay, so 2.53 times 10 to the 3rd meters, or 2,530 meters, okay, would be our wavelength here. Okay, so that should be practice, hopefully. Converting between energies and frequencies, wavelengths, okay.